Hi, everybody. Hello. Well, so I am Dead Program. Some people call me Ron. 2 humans call me Dad. But on the internets, Twitter, GitHub, Instagram, all the places, I am Dead Program. And I am a technologist for hire. With me is Salvador Evans.
AKA son of Dead Program. I am his apprentice number 2.
And I work with a little company called the Hybrid Group, where we are all technologists for hire. I was told to go subtle on this one. So we've done a lot of work for clients like Intel. Thank you very much for Intel for helping sponsor so much of my work. And for a little company out of Boulder, Colorado that had something to do with Wars in the Stars, as I've told you before, and that's still all I'm allowed to say. But we've done a lot of cool open source work as a part of that. GoBot, which is a talk I gave at the very first GopherCon. A few people remember that. GoCV, which I was fortunate enough to give a talk about last year, which is computer vision using Go. And then a really exciting project that I've become involved with this most recent last year called TinyGo. It's a Go for small places. Because everyone says Go is too big, right? It just goes fast, Go is portable, but it's very large as far as executable file size is concerned. So there's some languages that are typically used for programming of embedded systems, which are the smallest chips that run things in the world, like your refrigerator or brake systems or other things you really care about. So C. No one ever got fired for choosing C for their embedded system. But C++, just lots and lots and lots and lots more C. Python, which is having a real renaissance in terms of embedded systems, and a lot of really cool work being done in the MicroPython and CircuitPython communities. JavaScript always pops up nearly everywhere. And then a language called Rust, which is just a little too hard for me to learn, apparently. Because I really like Go. I mean, that's why we're all here, right? We really like Go. I mean, if you don't like Go and you're here, I'm sorry, really. But you said that everyone else said that they told you that Go was too big. Well, I'm going to show you right now that Go can be tiny. So hello world in Go, just a quick refresher. We have package main, we have a function main, and then print line hello world, all right? So hello world using Go 1.12, the most recent release, versus hello world using TinyGo 0.70, which is our most recent release. So let's go back to so if we say make hello. So I just built hello world in both languages. You see Go build and then TinyGo build, pretty much almost the exact same syntax. Yes, we copy from the masters whenever possible. And so if we run these programs, we see hello world Go says hello world. Okay, that's not very exciting, but it is what we expected. And then hello world in TinyGo. I don't know where that came from. Hello world. Yes, okay, it does work. But the interesting part is the size. So hello world in Go is about 1.1 megabytes, and hello world in TinyGo is 12K. How can you do that? He cheated. Yes, that is right. Anybody know what this is? This is the first film made by IBM Research where each one of these pixels is actually an individual atom. Not quite that small. Let's scale it back a little bit. Let's clear up one thing right now real fast, which is TinyGo is not the same thing as the full Go. I bet you guessed that right away, didn't you? So TinyGo does not support the entire Go language yet. Most of it, actually, as of the most recent release. TinyGo does not support the entire Go standard library yet, but actually more and more of it all the time. But TinyGo can do a lot already, and TinyGo is already very useful for small places, like microcontrollers, those smallest of chips, and WebAssembly, where Johan Brandhurst gave a talk yesterday that I was actually too busy to attend. I'm sorry, I was in the lab. But he's one of our team members of TinyGo and has been doing really exciting things with WebAssembly along with some others. So how TinyGo works, just very, very briefly, it's Go, TinyGo, and LLVM. So the Go compiler toolchain, that turns out is written in Go, which is a really fantastic decision. And the standard library includes packages that let you parse Go and turn it into its constituent most minimal parts, what is known as Go SSA, or Single Static Assignment Form. Then LLVM is a set of tools for actually building compilers. You may have heard of it. It's the basis behind a language called Swift. It's also the basis behind a language called Rust. Other languages like Zig, so it's a very robust and important set of tooling. It's been around for many, many years behind the scenes. So TinyGo is taking the source code in Go, passing that through the Go standard libraries to create the SSA form, then using the LLVM toolchain by converting the SSA to LLVM intermediate representation, then compiling that with Clang and LLD, which is the standard LLVM toolchain, to target it for all sorts of processors and environments where, until now, Go is just too large to go. So the hello world of things is always a blinking LED, and for that I'm going to start out with an Atmel AT-Tiny 85, also known as a Digispark. Digispark, please.
Tiny. Well, here you go.
Thank you. Chip off the old block. Oh, yeah. So let's turn on the camera. I knew I forgot something. So I'm running a Go CV program for my camera because it's all Go all the time in this talk. So this right here is, yes, thank you, it does work. So this is the Digispark. It's really, really small. It basically has to plug into a USB port to be flashed. So let's go and actually flash it. So I'm going to say make Digispark, and that is going to run TinyGo, compile it, and get it ready to be flashed. And if I insert this into my USB port, it erases and puts onto this 8-bit processor that has 8K of RAM, a Go program that I have just compiled. And let's go to the camera so you'll notice no cables, nothing up my sleeves, no sleeves really. I'm going to plug this into the battery. And it's going to start blinking in a minute. It's very small, so I brought an LED, which is actually larger than the Digispark, so you could see it, because sometimes it's just too small. So here we go. TinyGo on an 8-bit 8K processor. Sometimes I feel like a guy who saw a flying object, like, they're already here, I've seen them. Now you've all seen them too. It's too late. All right, so let's do a little bit of input and output. But wait, let's take a look at the code for a brief moment. So package main, same as you would expect from any Go program. We import the TinyGo machine package, which is our hardware abstraction layer, and the time package, which is compatible with your normal Go standard library. Function main, we say LED equals machine.led, right? That's our reference for that little LED. We configure it as an output pin versus an input pin. And then for ever, first we turn it off, sleep for 500 milliseconds, half a second, turn it back on, sleep for another 500 milliseconds. So it's a very, very simple program, but we see it works, and it does compile down to, I think, 342 bytes. Yeah, we have plenty of room on that thing for lots more code. All right, so let's do some quick input and output. So for this, we're going to use the Adafruit Circuit Playground Express plus an LED plus a button. So the Circuit Playground Express, please.
I don't have a pun for this one, so here you go.
Thanks. We'll work on that. Okay.
Sorry, I let you down.
So this is a very, very simple little board that it just so happens is actually the same board as the one we used in GopherBot. GopherBot, please.
Well, I don't have a pun for this one either, so.
GopherBot kind of speaks for itself, so I'm going to unplug this cable here. So this is the exact same board. It's just wired in. It's got some built-in buttons, and then we're going to use the LED that's on the springy antenna as when we push it. So let's plug it in through the little built-in USB port, and then let's take a very...
The other way.
Oh, thank you. Proof of fifth dimensionality. So I'm going to double-click this button, which puts it into its flashable mode. It uses something called the Microsoft UF2 standard for the bootloader. Oh, yes, thank you. It's ready. So that bootloader is Thank you. So if we say make button, it's going to compile and then flash it right on just by copying the hex file to the drive, the UF2 standard. So you'll see that's a 16K program, which in TinyGo terms is relatively large, but it also includes all the USB coordination. This program is pretty simple. Same as before, package main, import machine, import time. We declare our pin like before. This is going to be machine.A2, which is the pin for the antenna, and configure that as an output pin. Then we have our machine.button.A, which is the A button on the Circuit Playground Express. We're going to configure that as an input. And then forever, if the button get returns something, in other words, it's been pushed, is high, then we turn on the LED. Otherwise, we turn it off, and we wait for 10 milliseconds in between. So if we go to the camera, and I push the button, you see the LED turn on. It's kind of dim. Let's turn it this way. No, then you can't see it behind your hand.
Ah, of course. That makes sense.
That was a good idea, though.
But how about up here?
There we go.
Sort of.
All right. Very few demos, lots of time. Wait, strike that, reverse it. So it's a great time to mention tomorrow is Community Day. If you don't know about Community Day, it is one of the most amazing things about GopherCon. This is our 6th annual hardware hack session. So 9 a.m. tomorrow, we're going to have a lot of hardware for what we like to call your choose your own hardware adventure. So you get to take home some hardware to actually start playing or continue playing with TinyGo. Thanks to Arduino, this year's sponsor, TinyGo powered by Arduino, we have 300 of the Arduino Nano 33 IoT boards to give to the people who come tomorrow to our session. And you don't have to stay all day. You can just grab the hardware and run. It's been done. But we prefer you stick around and actually learn something and we'll get you set up. We also have drones and DIY robocars. But I forgot to mention to the organizers, we have boards already earmarked for the Diversity Scholarship recipients. So if you're not going to be here tomorrow, find us at lunch. Just look for the sign of the Gopher bot, and we'll have those boards for you all. Please tweet using TinyGo, hashtag Arduino, and hashtag GopherCon to thank Arduino for their generous sponsorship of our hardware endeavors. Thank you, Arduino. On with the show. So the Internet of Things, they're only Internet of Things if they have internet on the things, right? So IP protocol is what that's all about, and that's a lot of the reason why we even use Go. So the Go standard library has this thing called package net that we all use. So does TinyGo have support for the net package? Not yet. But we have a lot of the work already done for net-compatible implementations of the interfaces that work with the Wi-Fi chip that's built in to the Arduino Nano 33 and other boards that use the ExpressIF ESP8266 or ESP32, which is alphabet soup for the most commonly used Wi-Fi chips in microcontrollers. So we also support the PAHO MQTT client, which if you've done any kind of machine-to-machine messaging, is really it's the Eclipse library official Go client package for MQTT communication. So I actually don't have time to show this today because I have too many demos and not enough time, but we have an MQTT sensor station that is one of the activities we'll do in our workshop tomorrow, based on the Arduino Nano 33 IoT board, which has attached to its UART this separate coprocessor for Wi-Fi. So we communicate between the microcontroller and this Wi-Fi chip, and then it connects via internet to the Internet of Things MQTT broker. So I don't have time to show you all of that today, but it's actually there. It is real. Instead, I'm going to build a flight controller, because as all of you know, I really like things that fly. And last year, I did some flying things, and my PlayStation controller ran into some problems. Can I have the flight controller joystick assembly? So it's used as a joystick, and the buttons that are connected to the Arduino Nano 33 IoT, and then also an OLED display so I can see what's going on, because can I have the joystick?
You destroyed my PlayStation controller.
No, this is not that, I swear. There's no parts in this from that.
No matter. No matter. You paid for it.
We all paid for it, son. We all paid for it. All right, so let's plug this in here.
Okay, you did it the right way.
All right, so anything happening yet?
I think so.
Okay. All right, so let's take a very, very brief look at the code. So we use package main again. We're using some of the Go standard packages like image color. We're using the machine package from TinyGo. Stirconv, yes, standard package, time. And then we're using the tiny draw and tiny font packages, which are created by one of our other team members, Conejo Ninja, Daniel Esteban from España. And he did some amazing work on all these different displays. So, and we're using the OLED display, which is the SSD 1306, which is a very common display you can get from pretty much anywhere. So our main function is we're going to use this I2C interface, or I2C, to talk to the display. And then we're going to start the Go routine to handle the display in the background while we talk to the joystick. Yes, we can run Go routines on 32-bit microcontrollers that have 64K of RAM. Yes. It's real, I've seen it. So we're going to initialize the analog to digital converter. And then we have the joystick, X and Y. And we're going to have 4 buttons, B1, B2, B3, and B4, which are connected to these various pins. And then we're going to read the joystick, read the buttons, and then just send that information out the serial port. So we're just going to spam the serial port with these messages. And then we have our display. We're going to initialize that, configure it, clear the display, and then repeatedly put the information on the display for the position of the joystick, the X and Y, and the different button states. So if we go look at the camera, and I move it a little tiny bit closer, so you can see the display here. So while I move the joystick, so that's all the way left, all the way right, top and down. And then when I push the buttons, you can see that the little button circles fill in. So yeah, I needed a heads-up display. That was why I had to do it to the joystick, son. I'm sorry. It was worth it. You'll see it. It was really worth it. So let's go and run the PicoCom so we can actually see some data coming out of it. And it's just a very simple serial protocol. Same thing, if we move the joystick, you see the numbers change. If we push the buttons. So it's the minimum viable flight controller. All right, so far so good. How do I exit PicoCom? Oh, yes, that's right. All right, so now let's build a full application of flight control. So this is pretty much the same demo that I showed in my last talk at GopherCon with a few very important modifications for this flight controller and some others. So it uses this flight controller I just built, the CV-based ground system using GoBot and the Tello drone. So yeah, we're going to bring in GoBot using the DJI Tello drone, which, drone please. So the Tello drone is a very, very cool, low-cost consumer drone. It has in it a special kind of chip, which is called the Mobidius X. Can I, Mobidius Neural Compute Stick, please?
Tron much?
Yeah, I Tron every day.
We're not sponsored. We just like it a lot.
So, so the Neural Compute Stick is just a USB version of this same chip. It's a processor with a RISC processor that specializes in doing fast neural processing, and so that's what the collision avoidance and other algorithms in this use. So I'm going to turn on the drone, boot it. So take the drone over to the agreed-on launch place.
Give me a second. Here you go.
So this is going to be using Intel's OpenVINO, which is an open source wrapper around OpenCV that we have support for in GoCV to do the, make sure the camera's pointed out. Okay. So OpenVINO lets us do the deep neural network that is going to do the facial tracking of this system. So here's a quick architecture. So the flight stick, as it was before, and then via the UART, we're going to communicate through UDP packets to the drone, and then we're going to receive UDP packets for the video. Don't have time to show you any part of the code, except I have to remember which button does which. Let's see. So we're going to read the joystick from the serial port, and button 1 is the targeting system. I mean, the launch system. Yeah, all right, that's good enough. I can do it. I should probably exit this video. I don't know, let's just leave it running. Let's just run it all and see what happens. All right, so, oh wait, we have to connect to the drone. Disconnect from Wi-Fi. Are you sure you turned the drone on?
You didn't tell me to turn it on. But I don't know how.
I think you should bring it back over here real quick.
Sure.
Thank you.
You're so very nice to me.
Oh, it is on. All right, hold on.
See, I did turn it on.
All right, I'll tell your mother you were good. Oh, there it is. All right, put it back in the launch location. Yes, we have to move along. We only have a few minutes left before they drag us off stage.
Okay.
All right.
Okay.
And the camera's pointing out. All right, so let's see what happens. So I'm going to run it using a cafe-based network, which is going to have some facial recognition and tracking, some new stuff that we've added recently. And let's see if it will. Joystick underrun error. Hello. We are still connected, right? Yeah. Oh, there we go. Yes, we've made a few special modifications. So let's see what happens. Launch.
Sadly, the conference didn't let us put razor blades on it. So. Or BB guns. Either one's fine.
Uh-oh. It hasn't tracked the targets yet.
It's not facing them.
It's not even doing anything. It's very boring.
Oh, it's flying now.
Oh, there we go. I better grab the joystick. Oh, I just exited the program while it's in flight. Luckily, we can run it again. That's why we use UDP. All right, yeah, this is much better. See, I told you it was going to work. All right, so let's see if we can find the. Whoa. It's searching.
You have to go closer.
You think so?
Yeah.
I'm not sure.
Get it real close.
Real close?
Yeah. Give him a buzz cut.
It hasn't actually located any humans yet.
You should probably go closer, I think.
How much closer?
It doesn't matter. It doesn't hurt that much.
All right, I think it doesn't want to go anywhere else. It really likes some people. I really have lost control again.
Wow.
I swear. I don't think I'll be the dead one.
You should let me do it.
I know, you're much better at flying things. Well, all right, let's just exit the program. It'll be fine. Here, go get the drone.
Really?
You know how to grab it, right? You forgot already?
I don't
know. No, not
know.
like that.
Dude.
This is what, if a drone ever tries to bite you, just grab it.
He should really teach me some of these things, because I'm his guinea pig. You don't realize.
You're not a guinea pig. You're a human.
I'm
All right,
a
so the
gopher.
future of edge computing. So the future is coming right up upon us. WebAssembly is the future. So we recently, in our new release, launched the TinyGo Playground. So the TinyGo Playground is located at play.tinygo.org, and it lets you actually compile TinyGo programs right in your browser online. And it has a whole board simulator. But RISC-V, we haven't run out of the buzzwords yet, so RISC-V support we've already got. So let's see if my other camera's still running.
I'll risk my hand trying to get your drone.
Yeah, I know it bit me. So this is a Sci-5 Hi-5 board, which is a RISC-V processor. It's the newest board from the Sci-5 company out of California, which this is the next generation processor. So let's plug it in. And let's see, did I connect to the GopherCon network? So it pops up in my browser, and if I go over to play.tinygo.org.
What was the name of it again?
The Hi-5. No, the board. So the TinyGo Playground actually lets us compile our code online. One of the supported boards already is the Hi-5 Rev B. And so if I put in low, it compiles it online using a serverless call. Yeah, we got every buzzword all at once in one actual demo. And it uses our board simulator to flash the LED. So I'm going to click on this flash button. And that's going to actually download the hex file with the RISC-V compiled code. So if I take that code and I drag it onto the Hi-5 board, it's going to flash that board with the actual RISC-V code. And here you go, here's your future. So that's all I got for you. It's been great. The future is here right now. Please join us at tinygo.org. Check out Ika, who's the original creator of TinyGo, is here at the conference. He'll be tomorrow at the workshop. Don't forget to come to Hardware Hack Day tomorrow to claim one of your boards. Diversity Fund recipients, please see us at lunchtime. And we thank you.